welcome to you. If you're back, welcome back. We've been doing this every Wednesday now for a while, 5 Wednesdays in a row. And today is number 4. We've got one more, a week from tonight. And both tonight and next week are devoted to the Ice Age floods of eastern Washington, which I didn't know much about when I moved here 20 years ago, and I've been learning more and more and becoming more and more enthusiastic about that whole set of ideas. And I know that out here we have a whole cross-section of people, from people who have not heard of the Ice Age floods to folks who come out on field trips and come to evening lectures regularly devoted to the Ice Age floods. So we'll try to please everybody today. I don't know if that's possible, but we'll try. Great. Let's do this. Let's have the Columbia River flowing north to south. Let's have the Wenatchee River coming in from the northeast. So we better get some cities here. Here's Wenatchee. Thank you, Northwest. You're attentive too. Wow. What's this here? That's right. That's Interstate 90. So we'll put Ellensburg here. We'll put Vantage here. And let's put Leavenworth in. And let's bring in something diagonally here. Moses Coulee. Moses Coulee. I'm not even going to write it because that's not a city. Okay, so that's going to be like a little mystery feature that might be part of our story. Okay, we got a sense of what's going on. There's a big ridge that separates the Kittitas Valley from Wenatchee. So north is that way, right? So we're thinking northeast, up and over Mission Ridge, and we drop right into Wenatchee. It's right next door. I got a confession to make. I've been teaching here 21 years. And until this January, I knew next to nothing about the geology of the Wenatchee area. I'm not happy to report this. I just didn't get over to Wenatchee much for whatever reason. But I finally found a paper. I found a paper devoted to, a geologic paper, devoted to the Wenatchee area. It was behind my file cabinet in my office. I was moving the file cabinet. I found this field guide written by Stephen Porter, a University of Washington geologist. Wrote it in the late 1960s. And he had this little sketch map I'm going to share with you on the screen that showed the Ice Age floods coming down the Columbia River. I knew that. Wasn't that excited about it, but I knew that. But he had Ice Age floodwater on his sketch map, 1969, creeping up the Wenatchee River, Ice Age floodwater, with icebergs in it, all the way to Leavenworth. And at the same time, he had glaciers, ice, coming out of the Stewart Range, flowing down to Leavenworth. So he created this picture for me, looking at this little sketch map, of Ice Age floodwater lapping up against a glacier in Leavenworth, where you buy taffy and bratwurst and stuff, right? So this kind of really blew my mind, and I got very curious about it. And since then, I've found some other things, and I've kind of fleshed it out for me, and I've gone out with Tom Foster, the guy who we've been making these videos with, and we cooked up a little Wenatchee episode, so I've got that to share with you. And I led a field trip just a couple days ago with some people there. So it's been on my brain a lot, and I want to help you out. So bedrock first. So you know that around the ridges here we have basalt. This is not new to almost everybody here. Basalt, basalt, basalt. And I want to draw a bedrock map, a very simple one. So I would like to do this. I know they're going to put a lot of lines on here. This is a line separating basalt bedrock. So everything over here is basalt. Basalt, you know, is Hawaiian-like lava flow rock. Basalt, you know, came out of fissures 17 million years ago, and by 12 million years ago, for the most part, those lava flows were done. But we have a stack of hundreds of lava flows. This is new to hardly anybody in here. What is new to maybe many of you is that we have an abrupt edge to that basalt. North of Ellensburg, it's Table Mountain. Once you get up on Table Mountain, the first ridge north of town, boom, there's the north edge of Table Mountain. It falls away, and you're into Older Rock. We actually did that with the Ellensburg Blue Agate lecture our first Wednesday together. But that boundary continues. Mission Ridge is kind of the basalt edge. And East Wenatchee, the cliff just to the east of the Wenatchee area, is that boundary as well. So we've got all these lavas flowing from these fissures in southeastern Washington between this 17 and 12 million years ago, flowing northwest and running out of lava right at this boundary. We good so far? So that means the Wenatchee area has geology bedrock that is more than just basalt. You drive up and over Blewett Pass. That's sandstone. You drop down to Cashmere, Peshastin, Dryden. Those hills on both sides of the Wenatchee River Valley, those are lighter colored rocks. So even if you don't think about geology much at all, you maybe just must assume that it's not basalt. It's light colored stuff. That's sandstone also. This is sandstone that is about 50 to 40 million years old. Older. That means before the basalts flowed in, there was more sandstone. Can you do that? Can you get the sandstone in your mind beneath these layers of basalt? In fact, people at the oil and gas companies who've been drilling, looking for natural gas, were up on the Saddle Mountains, up on the crest of the Saddle Mountains, drilled 12,000 feet. I repeat, drilled 12,000 feet and finally got to the bottom of the basalt lavas. And what did they run into? The sandstones. So those sandstones do extend beneath the basalt, but this is not a minor blanket of basalt. This is more than 12,000 feet, at least over here in the Othello area. Okay, there's more than sandstone. Just north of Wenatchee, and this is going to be part of our Ice Age flood story actually, just north of Wenatchee, Gneiss. That's right. You guys are geologists. You know how to pronounce that. Right. Gneiss. That's how you pronounce it. Gneiss. Gneiss. That's a metamorphic rock. I'll show you a couple photos. That's 1 billion with a B. We're not talking about federal deficit now. We're talking about age of this rock. 1 billion. For that metamorphic rock just north of Wenatchee. And there's a very sharp boundary between the sandstone and the 1 billion-year-old metamorphic gneiss. I feel like I need to shake things up a little bit. I haven't really laid anything really earth-shaking on you yet. No pun. I got to cut to something really good. You ready? This gneiss was not created in North America. Our current understanding of this 1 billion-year-old gneiss is that it belongs to somebody else. It is somebody else's Precambrian basement rock and was somehow moved from somebody else's basement to the edge of North America. We've got our own basement. Our own basement goes from Moses Lake all the way to the Appalachian Mountains. We have a Precambrian basement. It's called a craton. But that gneiss and a whole series of other metamorphic blocks in the North Cascades are terrains, exotic to North America. Pieces of rock that have been moved from the Pacific Basin to here. Now, we're a long way from the Ice Age floods, but I just want to stir the pot just a little bit. And if you're new to us, my credibility is taking a hit now, because that sounds almost impossible to believe. Almost impossible to believe. But that's our current view. Now, the obvious question is where to come from. Whose piece is it? Is this a piece of Antarctica? Is that gneiss north of Wenatchee a piece of Alaska that got sent back down here? We don't know. We're looking for the match. Nobody's getting rich looking for the matches in these things, so it takes a while. But the point is, we have more than basalt for the Ice Age floods to deal with. We have basalt, sandstone, and gneiss. Okay? Great. Now, let's draw a quick stratigraphic column using these three ideas and draw a quick cross-section to help that out. And then we'll bring the Ice Age floods in before we go to the images. All right, so down at the bottom we've got our 1 billion-year-old gneiss. Let's put an asterisk behind it. not ours, okay? It's foreign. On top of it, sandstone, 50 to 40 million years laid on top. On top of that, what? That's right, basalt, 17 to 12. Yeah, that's pretty boring. Let's make it more interesting. The layers aren't flat anymore. The layers have been folded. No surprise, we talked about that last week. Layers originally flat and then being warped due to moving tectonic plates. So now, when we realize that we have both gneiss and sandstone in the Wenatchee River Valley, which is really where we're going to put most of our attention, let's draw what it really looks like in cross-section today. Here's the gneiss, here's the sandstone, here's the basalt. In other words, there has been some significant folding of the sandstone layers and the gneiss below. So we have anticlines and synclines, upfolds and downfolds of not only the sandstone, but the gneiss down below. Gneiss cored anticlines, if you want to be fancy about it. Gneiss in the core of these anticlines. And in places on the previous map that we could see that gneiss was a place that we had eroded all the way through and gotten down to this gneiss and actually brought it to the surface so we could take a look. One of my big points is when you go to the Wenatchee River Valley and you see sandstone, and we'll see it visually in a bit, the layers of sandstone are almost standing on end. If you go to the Peshastin Pinnacle State Park, where you get $99 parking tickets, long story, but that was Sunday. Okay, great. The sandstone layers were originally flat. They have been taken from their original flat, and they have been warped around these upfolds. So if you go to the pinnacles, or you drop down any place in the Wenatchee River Valley, you'll see sandstone, but if you look carefully, there are slabs that are tilted almost 70 degrees in many places. That's from this folding. Most of places, the basalt is relatively flat. Relatively flat. It's called Table Mountain because it's pretty flat up there. But there are some places where the basalt has been folded as well. So I'm getting a little bit too into the structure here. I just want to give you the impression that there has been at least one batch of folding, in some cases, two batches of folding. And some of these folds or crusts of these anticlines you can match from the basalts through the sandstones. I can't hold it. I got to do it. I got to do it. I wasn't going to do it. I'm going to do it. I don't care. I don't care. I got to make this map again. It's not going to look anything like the first one. Columbia River, yeah, that's pretty good actually. Okay? Wenatchee River coming in from the northwest. Columbia River. What's this again? Moses Coulee, correct. Vantage, Ellensburg. Good. Wenatchee. Here's the last thing I want to say about these folds. Look at a map sometime. The Wenatchee River Valley has a trend, a northwest-southeast trend. Look carefully at the folds in these anticlines, in the sandstones. There's a northwest-southeast trend. Remember our ridges south of Ellensburg last week with the Yakima River Canyon? Who was here first, the river or the ridge? What was the orientation of those guys? Northwest, southeast. This is a repetitive story that continues even out into the basalts. This was new to me, one of the new things that I realized. Our ridges in the basalts continue, the folds continue into these older rocks. They don't show that beautiful ridge pattern like we can obviously in the basalts, but they're there. There's a structural fabric here that is telling us about that clockwise rotation. We're not going to go through it again this week, but if you're with us last week, you remember that there was a clockwise rotation of the Northern California, Western Oregon, Southwestern Washington, and having all of this stuff being compressed recently. Okay, finally we get to the Ice Age floods. And I want to do just a little bit here because these images and these videos that I have for you tonight will really make the story sing, I hope. Now we're jumping to 17 to 14,000 years ago. 17 to 14,000 years ago. I think we got to recalibrate our brains now, right? We were a billion with the gneiss. Our youngest stuff was the basalt, which was 17 to 12 million years ago. Now we are much, much less than 1 million, right? We're just yesterday geologically during the Ice Age. Now we realize we have ice, a major ice sheet covering all of Canada and down into the northern part of Washington. And the ice is starting to retreat. It's starting to melt. And fresh water is ponding along the front of the ice. Again, let's have the maps that are professionally done tell the story. What I want to do is, Ice Age floods that came into the Wenatchee area came right down the Columbia River. I repeat, Ice Age flood water that entered the Wenatchee River Valley came right down the Columbia River and right over the city of Wenatchee. Water that's 1,000 feet deep, 1,000 feet deep, coming down the Columbia River 60 miles an hour. Fill the Columbia Valley with water and have it come down the Columbia, now over Wenatchee, around the corner, around another corner, down through Vantage, and on the way down to the Tri-Cities and eventually out to the Pacific Ocean. That's the main story. That's what I'd known for 20 years. What I never thought of is if you have 1,000 feet of water coming down the Columbia River, that water has to negotiate this curve. That water has to fill this little broad valley that Wenatchee sits in, and our Ice Age flood water is going to start creeping up the Wenatchee River Valley. The blocks of ice that are floating in that water are broken off pieces of the glacier ice sheet to the north. And we incorporate that because we have big erratics, big boulders that were moved by the Ice Age floods. They floated those rocks right in. So, to keep track of what's going on, I'm almost done with the chalkboard stuff. The main message is Ice Age flood deposits in Wenatchee, not erosion. Ice Age flood deposits in Wenatchee, not erosion. And that comes in three forms. Ice rafted erratics. Ice rafted erratics, as opposed to other erratics. How else do you get erratics? You get it from glaciers, ice-moving boulders. So we got to figure out how to tell the difference. The second main way that we're going to deposit stuff out of this water is when the Ice Age floods come around a curve. We're going to have a flood bar, but it's going to be a giant flood bar. A giant flood bar. The biggest giant flood bar, the largest flood bar in the state, as far as I'm concerned, I don't think this is a controversial statement, is right at Wenatchee. There's an enormous flood bar, 600 feet high, a bunch of loose rocks dropped by the Ice Age floods, rocks that were brought down the Columbia by this 1,000-foot column of water and dropped as this water slows and negotiates this turn. Pangbourne Bar, it's called. All of East Wenatchee built right on it. I'll show you images. And our last idea is when we get this water to stop, if we slow the water down and get it to stop, and where are we going to do it on this map? We're going to do it in here, right? This is a little side channel. We don't have massive flow through the Wenatchee Valley, but if we can get the water to stop, I always have trouble with that. R-H-Y-T-H-M-I-T-E-S. Rhythmites. A rhythmite is a layer of fine-grained sediment, the bottom of a freshwater lake. So if we have this water coming in here and sitting still, all the silt All the fine particles are going to have time to snow out, to drop out the bottom of this standing water, and we're going to get an actual deposit. One deposit for one flood. But what if you have 25 layers? Like we do in the Wenatchee River Valley. Beneath all those apple orchards in the Wenatchee River Valley, that's a beautiful place for trees because they're built on these rhythmites. They're built on these Ice Age flood deposits. If there's 25 of these rhythmites, we have 25 separate times when we had water surging up that valley. So we're looking at Wenatchee. We are looking west over the Columbia. Here's the Columbia flowing from north to south. Here is the Wenatchee River heading up into the Cascades as far as Leavenworth and beyond. That's the setting for our drama. Now, let's do this bedrock thing, but with visuals this time. Can you handle this? There's a lot on this. Here's Wenatchee. Here's the Columbia coming down and doing that curve that I had on the chalkboard, right? Here's the Wenatchee River coming in from the northwest. Major rock types. This is an oversimplified geologic map. Let's start with the metamorphic gneiss that is just to the north of Wenatchee. Here's what a gneiss looks like. It's metamorphic. It has biotite within it, which is black mineral content. And there's organization in the rock. The black and white minerals are lined up parallel to each other because of squeezing. There's high pressures involved. This is the 1 billion-year-old rock that's somebody else's. And last Sunday, we had people out sitting on that exotic rock, and we talked about how far that metamorphic gneiss had traveled. These guys are sitting right north of Wenatchee on a beautiful Sunday afternoon. The sandstone, which dominates not only the Blewett Pass area, but from the Columbia River stretching all the way into the upper Kittitas County. We're talking about the rocks of Roslyn, the coal-bearing deposits as well. This is a time when we had a flat area with lots of sand accumulating, probably in stream systems, some lake systems. And it's just a bunch of sand, still today. Turns out it's an arcosic sandstone, which means it's got a variety of sand. It's not all the same type of mineral content. But as promised, when you go to Peshastin Pinnacles or other places where there's this beautiful sandstone, and again, we are between the cities of Wenatchee and Leavenworth, everything's inclined. This is a place to climb because those sandstone layers have been tipped almost on their ends. Let's go back over here to the more familiar basalts. And just on this Google Earth image, you can see how much of a plateau this is, how relatively horizontal these layers are, and how the drainage patterns look very different over there. This is what a normal basalt looks like. It's dark colored, right? The lava rocks around here, you've all seen them, with occasional minerals to look at and identify. That's what's going on just south of Wenatchee. So here's our friend Moses Coulee, which has been a peripheral part of our story today, but I was careful on the chalkboard not to draw a river in Moses Coulee. If you know about Moses Coulee, has it dawned on you that this is one of the largest canyons or valleys in Washington, and there's no river in it? Like not even a hint of a creek? Like nothing. How do you do that? You got to come next week to find that out. All right. Right here in the middle, smack right dab in the middle, with all of our bedrock on all sides, here is our giant flood bar. 600 feet of rock filling this entire area between the Columbia River and this major cliff off to the east from downtown Wenatchee. More visuals to come to help you. But those white areas are showing us the Ice Age floods coming down the Columbia River. And here's a spoiler from what I just said. Ice Age floodwater coming down the Moses Coulee. That's how Moses Coulee was created. That's probably not a surprise to you all. And if you dig into these giant flood bars, like Pangbourne Bar, the giant flood bar in Wenatchee, you've got all of this loose rock. Look at the scale of this. Just a pile of rocks like dropped out of heaven. Where did they come from? And they're not basaltic, so they had to be traveled long distances. And they're all big rocks. You got the Ice Age floods doing that. I got to fess up, this is not Pangbourne Bar. This is a giant flood bar closer to Trinidad, or Crescent Bar, if you happen to know that area. So for those that are in over your heads already, you're feeling like you didn't get on the ground floor in this Ice Age flood story, let me give you a quick crash course. This is from space. Here are the Cascades. Here's our friend, the Columbia River, Tri-Cities, and then out through the Columbia River Gorge to Oregon. And these dark-colored veins here are the Ice Age flood paths. Only viewed really properly from space. Glacial Lake Missoula, you've heard of perhaps. Glacial Lake Columbia, large pools of fresh water against a retreating, warming ice sheet. These are the Ice Age flood paths, and we are way over here on the margins. I don't feel that bad about not knowing Ice Age flood stuff in Wenatchee. It's not in the main game. We're way over here on the edge. And yet, we're focusing on how impressive those features are. This is a beautiful map from the Ice Age Floods Institute, showing us exactly where that glacial Lake Missoula was located in Montana, behind an ice dam in northern Idaho, and often overlooked is a second glacial lake in northern Washington, Glacial Lake Columbia, created by the Okanagan Glacier that ponded water there. The dark areas are the places next week where we will have incredible outbursts of water digging into the ground, creating waterfalls and coulees. Palouse Falls, Dry Falls, stuff like that. But that's not us this week. This is back in Montana, just giving you a feeling of the scale of this. Everything in the valley here was under a lot of water. That's where we had the reservoir to get all this water together in Montana. If you've been to the University of Montana and the capital M behind campus, all these marks on the ridge are high water marks of that glacial Lake Missoula during the Ice Age time. So, get the water ponded, get an ice dam in place, get enough water in the lake to finally overtop or undercut the ice dam, and we release the hounds over eastern Washington, including coming down the Columbia over Wenatchee. Not every time, but often enough to create some impressive features. All that water coming over eastern Washington has to squeeze through one place, Wallula Gap, a narrow gateway to the Columbia River Gorge. We're down at the Tri-Cities now. Every drop of Ice Age floodwater has to get through this gap, and they all can't go at the same time. That's why we had the water stopped again. Remember, it was stopped in Montana, right? Then released quickly, now stopped again. And creeping up the Yakima drainage, that's what Suzanne and Bob were talking about, rhythomites at Zilla, and rhythomites all over the place, or Chukchi beds, or Ice Age flood deposits, however you want to say it. And this is the visual then. We're not in Wenatchee yet. We're just laying the main story. This is a photo of the Tri-Cities with the exact high water mark at 1250 elevation of Lake Lewis. I mean exactly how high that water was, waiting its turn to go through Wallula Gap. Beautifully reconstructed by hours and hours, years and years of field mapping. And eventually the Ice Age floodwaters come all the way through the Columbia River Gorge between Oregon and Washington. Here's the Vista House, some of you know. The Ice Age floods were higher than the Vista House, coming through the gorge. And eventually the water, it's like a Disney movie, it finally gets home. It gets out to the ocean and the story's done. Here is a simulation of the floods coming over eastern Washington. This is mathematically derived with using some very fancy math. And the colors are the depth of the water. So here's our Lake Lewis getting green and then yellow and then orange as everybody's trying to squeeze through Wallula Gap, and then we've got water also ponding in other areas as well. We're talking about Wenatchee today, which is actually protected for much of this time by the Okanagan Glacier. So one reason that the Wenatchee Ice Age flood story is not erosive is because this big Okanagan Glacier was in place to protect Wenatchee from much of this action. When the Okanagan was here, the water was shunted down the Grand Coulee and over Dry Falls. So put it this way, when we had massive ice aging flooding at Dry Falls, which we'll do next week, we didn't have any action at Wenatchee. But when this Okanagan Glacier goes back, then the water can leave the Grand Coulee and go right down the Columbia. really beautiful, really simple. That's my specialty, making it as simple as possible, although trying to be true to the facts. So again, the familiar view, the dark telling us where the Ice Age floodwaters, I just ignored this. It just didn't even really occur to me that we had our Ice Age floodwaters coming up the Wenatchee, but we're going to do that right now. Let's go there. So here's this thing I found in my office behind my file cabinet. It was donated to the department by William Prater. Bill Prater was a mountaineer, and a famous one at that, and was heavily involved in our outreach efforts here in town, and decided to give this to the department. I appreciated it and then lost it. Happily I found it behind my file cabinet. This is that sketch that got me charged up. Let's just take a moment to look at this. This is Wenatchee. This is Steve Porter, University of Washington, the late 1960s. And yes, he's talking about Ice Age floods coming down the Columbia, but here's our backwater. And here's our glaciers. This is Blewett Pass right here. I was just drawn in by this simple but beautiful sketch. So I took Porter's work, and I took another guy's work, William Long, who worked for the Forest Service. Long actually went into this area and found erratics and mapped them carefully to combine with Porter's work. So I had this map specially done a couple weeks ago. Jennifer Hackett lives in town, and she creates map using fancy programs, GIS and things like that. So thanks to Jennifer for that. We used this map on our field trip on Sunday, and we're using it again tonight. Everything in purple is under Ice Age flood water. Columbia River, Wenatchee's here. Great. Here's exactly where our Ice Age flood water is creeping up Highway 2. Cashmere, Dryden, Peshastin, Leavenworth, even creeping up 97, a little bit towards Blewett, which is down over here. And ice coming down the Ingalls drainage, ice coming down the Icicle drainage, heading right over Leavenworth. Okay, what evidence do we have specifically for this ice? We've got a little bit more work to do. That's the main story tonight, but there's some fine-tuned details we got to put in. If you want to prove to somebody that we've got glaciers coming down into a landscape they no longer are in, we need to look for glacial rocks, glacial till, poorly sorted rock coming from the mountains, and specifically ridges of those glacial rocks called moraines. We do have those in the Leavenworth area. Give you a chance to get your bearings here. Can you figure out where you are? Here's Leavenworth. We're looking kind of obliquely to the southwest. Here's the Icicle drainage, Mount Stewart and the Stewart Range up off the screen. Here's 97 coming down from Blewett and hooking up with US 2, so Wenatchee goes this way. Got it now? So these ping pong balls here are my way of showing where the ice used to flow. Ice coming down the Ingalls drainage, hits the Peshastin Creek, gets to here, end of the line for the ice. Same thing for all these guys coming down over Leavenworth. Now how do we know that? The ice is gone. There are moraines, yes, there are beautiful moraines mapped by Porter in the late 60s. But we can also look at the type of rock that was moved. This is not granite, technically. Most of us would call this a granite. This was on somebody's countertop, all polished, you'd call it a granite countertop. But if you cared about geology specifically, this is a granodiorite because we have a little bit too much black mineral content for a good-looking granite. Granodiorite, a little bit more black mineral content. And this is what dominates the Stewart Range, 93-million-year-old granodiorite that the glaciers, the ice, are bringing down from the Stewarts down to Leavenworth and down to 97. Now this should look different to you, does it? This is truly a granite. Let me go back. Granodiorite, more black mineral content. Granite, less black mineral content. I was hanging out the lab room this morning, taking photos out the window of Linda Hall. Probably too much sunlight, actually. This must be a different source. We're going to use this right now. So these gold stars are ice-rafted erratics. These are true granites that came from up north. Possibly, if you believe Long, some of the granites from northern Idaho coming down and being flushed up here on these ice rafts. But the granites, in quotation marks, coming down from the Stewart Range are the granodiorite. So if we put them side by side outside of our mudroom, you can see the granodiorite looks different than the granite. Why do we care about that? The source Stewart Range is going to look different than stuff coming down from northern Washington or Idaho. That means we can say if we have a big erratic in the Wenatchee River Valley that is granodiorite, it was brought in by ice from the Stewart Range. If we find these guys, we can do a much more dramatic Ice Age flood story. That's the main gimmick. That's the main story. This is orchard country now. Everything purple here are these rhythmites with these big boulders. Next time you go to 97-2, look for these erratics. They're all over the place. I think when they redid that intersection a couple of years ago, they found a bunch and just tossed them up on the side. So they're all over the place if you look for them carefully. Here are some more beautiful ones photographed by Tom down in the Columbia River Gorge. I mean, if you know nothing about geology, I would think you'd be at least a little bit curious about this giant white rock where there's nothing but brown rock everywhere you go. What's up? I would think that. Our model is not only being carried by the Ice Age floods, but rafted on these Yukon Cornelius-like icebergs. Ice rafted erratics, that's the main story, but it gets a little tricky because I think it is possible with the velocity and the volume of these Ice Age floods it's also possible to tumble these guys, to roll them along the floor of the flood channel. They don't have to be rafted. So how do you make a call on the difference between erratics from the Ice Age flood that were rafted versus tumbled on the bedload? Let's have one of the best guys to figure this out help us with this. This is a short interview clip from KCWU-TV.
Now, the question of whether it was moved along the stream bottom or as an ice rafted block is a little more difficult. But in that one, you sort of have to think, just how does the flood work? Mechanically, the thread of high velocity in the floodwater is through the center of the channel or across the center of the fan. But floating material or debris, anyone who's observed water in a flood will see floating logs, and these will move off to the side of the channel. It's caused by the shearing of the water flow. Another way you can think of this is if you were pretending to be the flood and thinking about how would the flood work, you would think about how you would be as an iceberg in this flood and where you would float to, and you float off to the side. It's kind of like the ring around the bathtub.
Yeah.
The dirt all goes off to the side and makes a ring, and that's where we find the icebergs. And we know from studies of many erratics that we find them concentrated in places like that. We don't find them in the middle of the channel. It's possible that as the flow dropped, but it would have to drop very fast. You could drop one there, but it would be a really infrequent chance. So what we find instead is that things in the middle of the channel have rolled along the bottom of the channel.
So you've heard of J. Harlan Bretz, who was the main person to kind of try to stubbornly convince everyone that these floods actually happened. He really passed the baton on to that guy, Vic Baker, and another fellow we're going to hear from in just a second, Richard Waite, who spent their career working on these issues as well. So now we're pretty clear. Ice rafted, not tumbled, because we're not in the main channel, and we've got these erratics off to the margin, like Vic was talking about. This is a handout from the field trip where we were looking at this whole story in a general context. Here's our first stop where we're looking at these rhythmites working their way up. So everything is light green, beautiful orchards near Leavenworth, Peshastin, Kashmir, etc. We want to visualize these rhythmites as being underneath. Now this is Zilla, not the Wenatchee River Valley. This is one of the best places to see what Suzanne was asking about. Each of these chalky white layers is a separate flood event. We now view more than 90 individual Ice Age floods coming across eastern Washington. Floods of different sizes. They didn't all cover the same amount of ground. But when you have this repetitive story of rhythmites, that's what we're talking about in Zilla, and that's also what we're visualizing for what is beneath those orchards in the Wenatchee River Valley. So from Sunday, we had some deposits. We'd be digging for them, but the exposures were not great. And you get the idea that this is really the kind of stuff that needs to be studied to further our understanding of the number of floods, now that we have the general story figured out. So ice age floods coming down the Columbia, water going up the side. I think we're now about to hear from Richard Waite, who's going to give us a sense of his contribution, which J. Harlan Bretz missed. So this main guy who back in the 20s and 30s was putting all this story together on foot. I mean, it's an amazing story if you haven't heard it before. He covered a lot of ground, J. Harlan Bretz, but he didn't spend much time in the Wenatchee area, so he left something for Richard to work on. A couple seconds from Richard.
Covered a gigantic bar at Wenatchee. I mean, absolutely huge bar where the airport is, Pangbourne Airfield's on top of it. And other bars.
Previously unrecognized?
Yes, it hadn't been recognized as a flood bar. And then started finding exposure. So the exposure, besides that flood, the big flood bar indicated there had been at least one immense, monstrous flood down the Columbia. In fact, the ice-rafted erratics above the level of the bar go up another several hundred feet. So, and the valley itself, past Wenatchee, does not seem to have been deep in any, little if any, since the Pleistocene. You can tell that from the way sediments are in the valley. So the water coming past Wenatchee at a fairly steep gradient of 7 feet per mile was 1,100 feet deep. I mean, so this was huge. I mean, this is huger than anything I'd read about anywhere on Earth, including the Channel Scablands.
The Chamber of Commerce and the Visitors Bureau in the Wenatchee area has caught wind of this Ice Age flood geology. And they've been proactive in trying to combine these two things to enhance tourism. So this is a brochure that's available, and it's laid out beautifully. Geologists have worked on detailed road maps of the Wenatchee area, telling people how to find these boulders, how to find these features that we've been talking about tonight, and north of Wenatchee as well. And you flip the thing over, and all of a sudden you're out east of Wenatchee. You're up on the Waterville Plateau and doing more Ice Age flood geology, which we'll be doing next week. So, nice piece of work here by the Wenatchee Visitors Bureau to put that all together. I hope that I have changed your view just in this photograph. Just from the work we've done tonight, in addition to a nice, pleasing photograph, we now can see bedrock. We can maybe see this Ice Age floodwater cruising through the picture, filling much of what you see, and depositing much of what we've talked about tonight. That's the beauty of geology, taking a place that everybody knows and adding to the enjoyment of it.